So we talked about the plankters having to adapt to the marine environment to remain afloat and to optimize their surface area to volume to deal with the viscosity and the exchange of nutrients and waste and oxygen and so on, right? But if you're a nekton and you are trying to move through the water, remember, unlike the bird flying in the air, which has a very low viscosity, water is a very heavy fluid and it has much more resistance when you move. So viscosity is much higher. So many streamlining adaptations are required. So here are some of the larger organisms like the emperor penguin, which has it's got tiny little wings which mostly walks on the land and swims in the water like a rocket, right? Can fly through the waters, especially when it's being chased by animals that want to eat them, right? Here is a leatherback turtle, doesn't move that fast but still can move fast in the water. You can see how it has streamlined its body, has its tail fins and the wings with which it can flap around and move around. Walrus, which looks big and fat, but actually it's quite streamlined for the water in which it can be found. And you have, of course, the bluefin tuna that I mentioned. Bluefin tuna is a fish, but its oxygen recirculating system, it's called rete mirabile. It's Italian word. I'm Italian, ragu. So it recycles oxygen within the blood to be a very efficient swimmer and to move with efficient use of oxygen. As I said, they can move at 70 kilometers per hour when they want. So they have this tapering, and this is one of the most streamlined bodies, right? Has these nice little micro fins and the tail fin and the top and bottom fins, just like an airplane with these side fins and so on, to reduce the turbulence around it and streamline and cut through the water and move that fast. You can imagine how good an evolution that is. The other thing that animals have to adapt to in the water is how they're going to spawn, how they're going to reproduce, right? Unlike the birds, which can put their eggs on a tree, in a nest, or in the ground somewhere and so on, these marine animals are in water unless they are these meroplanktons which can use the bottom to lay the eggs like the squids do. They have to lay the eggs in the water, so they have to make sure that the water doesn't let the eggs disappear and are not eaten by other predators, and the larvae, when they hatch, can find the food, and so on and so forth. So there are many optimizations or many strategies needed to reproduce. And they also have to decide whether they're just going to spawn when the conditions are good enough, or they need to find very specific conditions. So there are many details involved there. There are two strategies called the K strategy and the R strategy, sardines versus tuna, for example, where the broadcast spawning basically means they are directly releasing eggs and sperms into the seawater, so that sperms and eggs have to find each other and fertilize the egg, like the pollen being released in the air. There are some where the bees and the pollinators, like birds, have to move the pollen, or the seeds can fly, and so on. So many strategies are required on land and in the ocean. But the ocean is special because the fluid is there is no habitat. When you're living as a pelagic nekton or a plankton, you have to find ways to survive. So marine organisms take advantage of the high viscosity to enhance the reproductive chances. The temperature range, as we said, is fairly narrow. The daily, seasonally, and year to year, the variations are relatively small, except in regions where you have these El Nino-like things happening. And the deep ocean is almost isothermal. Remember the thermocline shape? It goes to almost a constant temperature below the thermocline. you can actually compare the range of temperatures you would get on land and in the open ocean versus the coastal ocean. Okay, so if you go into the open ocean, you get the entire range going from about -2 degrees centigrade to 32 degrees centigrade. The range is 34 degrees. Why is it -2 degrees centigrade? Why doesn't it freeze? Now you remember your concept. If you add salt to the water, the freezing point is lowered, is decreased, so it doesn't freeze at 0 but can go down to -2, and if it freezes, the ice is going to float, right? So deep ocean can be as cold as -2 degrees centigrade. Coastal ocean is shallow, it's constantly being mixed up by the winds and fresh water coming in and so on and so forth. So its range can be larger because it can warm up faster and cool down faster because its heat capacity is not as large as the open ocean. So its range is a little bit higher, going from -2 to 40 degrees centigrade, whereas on land the heat capacity is low, so it can freeze down to -88 degrees centigrade. That's colder than Mars, right? If you go on places like Antarctica and the Arctic Circle and so on, with the winds and so on, you can create -88 degrees centigrade and a maximum of 58 degrees centigrade in deserts and Death Valley and so on, right? So the range here is 146 degrees centigrade. This also explains why we have so many species on land and so few species in the ocean water. Okay, so ocean temperature is more stable, high heat capacity. Ocean warming is also reduced by evaporation. If water gets warm, it begins to evaporate more. Evaporation breaks the hydrogen bond, takes the energy from the water and cools down the water, right? Solar radiation penetrates into the ocean, can go down to more than 100 meters, as we will see, and the ocean is constantly being mixed. The land cannot be mixed easily. You can have soil moisture loss and a little bit of cooling, but mostly land has much less mixing possible. So these are kind of the various properties that affect the evolution of life in the ocean, and that's the contrast from the ocean to the land, which determines number of species and speciation or evolution of new species as conditions change.